Hello everyone. So this is going to be the post-contest discussion for weekly contest 394 for the Leetcode platform. All right, and we'll be discussing all 4 problems today. So let us try to read the problem 1. You are given a string word. A letter is called special if it appears both in lowercase and uppercase in the word. Return the number of special letters in the word. All right. So I think problem is pretty easy, right? First problem is definitely very easy. Simply they are telling you that you will be given a word. All right, some characters are made of that word. Let's say the string, there's a string S1, S2 letter, S3 letter, S4 letter, and so on, so on, so on. And then for each and every combination of lowercase and uppercase letter, you have to see whether they both exist or not in the string. So if I say small a and capital A exists, then I say answer plus plus. Same goes for if I say small b and capital B also exists in the string, then I say answer plus plus again. And so on, so on, so on. I do this for capital Z and small z pairs. So all 26 basically, right? So I think this is like definitely a very easy problem. If you look at the test cases, things become pretty clear, right? Small a, small b, small c were there, but corresponding to them, capital A, capital B, and capital C were also there. So the answer was 3. Similarly, in this answer was 0, and similarly in this answer was 1. Alright, so now the length is also given very small. So you can definitely brute out everything, right? You can apply a very simple solution, and there can be multiple answers definitely to this, just to find out whether you think there is existence of the small and the capital letter also. So in my approach, what I have done is, simply I'll say, let me create 2 vectors of 26 size. Alright, I will name the first vector as the lowercase indexes. So I'll call this lowercase c something, and I'll have this of 26 size with -1 index initially initialized to everything. And I can similarly say this for the uppercase letters also. So this becomes again 26 comma -1. And now what I'll do is I'll iterate in the word, and every time I iterate in the word, whatever current index I am standing at, I am going to mark whether if that index letter is a lowercase letter, then I'll mark its index in the lowercase so as to accommodate 26 positions. Else I'll do that in uppercase. So if I think that the current letter is lowercase, then I'll put that in the lowercase array. Else I'll put its index in the uppercase array. Simply just storing basically that whether I think this letter occurred or not. Right? So occurrence is the main key. Occurrence of storing of that letter is the main key. Now what happens next? Very simple. You can now iterate back in the, I think you can iterate 26 times with an iterator in the lower and uppercase array simultaneously. And if you think that at the current index I, you find that both lowercase character array did not have a value -1 and uppercase character array also did not have a value -1, then you can very well say that this current letter, by the representation of in the ASCII value, you can call this that, let's say I was standing at current index I, then I minus A, or you can even call this I minus capital A, right? ASCII value difference. This current letter is definitely a letter that is existing in its lowercase format also and its uppercase format also. Alright, why is this going to work? What happens over here? In this case, what happens is, let's say this is not I exactly, this is word of I. What happens in this? What do you mean by when I say word of I minus small or word of I minus capital A? What the language does is, it calculates the ASCII value of word of I. Yes. And then it subtracts from that ASCII value the ASCII value of small letter a. So let's say the word of I was, let's say B. Then B minus A would actually have been in ASCII values, I think this starts from 97, so this is 98 and this is 97. When you subtract both of them, you get 1, which indirectly tells you that this is the second letter, or if you second letter in meaning of, let's say, 0 base indexing, or simply calling this as the letter B that could have come in representation of lowercase letters. And similarly, if the letter was B, capital B, and from that you subtracted capital A, then this would have been, I think ASCII values are for this is 68, 68 minus, 66 minus 65, this would again have given me 1, giving me the value which I could have actually incremented in this uppercase array. So this is basically simply creating frequency map, right? I have just thought of a method to create frequency map with a vector format. You can definitely implement this with maps, unordered maps, because the total length of the word is so low that even if you apply a map or an unordered map, you're not going to achieve a very high complexity. Target, the idea is to actually calculate the frequencies of every or even simply saying occurrence of every letter in the lowercase format and occurrence of every letter in the uppercase format. And if both exist simultaneously, increase your answer. Alright, so this is just a rough part of implementation. Implementation for this question could have been done in multiple approaches. So now, according to my approach, what will I now do? I would have let's say this is the word A, capital A, small b, capital C. So this is 0, 1, 2, 3, 4, 5. These are the indexes. Yes. And then I would have had a lowercase array which would have all negative ones initially, till 26 times. This is lowercase, yes, lowercase. And similarly, I would have a negative one all initialized array of 26 size, which would have been actually the uppercase. Now, I would have iterated in this string from left to right. I would have stood at, let's say, the letter A. So I would have said, all right, is this letter small? I would have kept a check. Yes, this letter is small. Since this letter is small, let me do this letter minus small a. That would give me the value 0. So I would mark in the 0th position of the lowercase array the current index, that is 0. Similarly, next time when it becomes, let's say, a, then no worries, because I just want occurrence. So if this gets updated with the new index 1, that is also not my concern. Now capital A, because being the capital letter, gets updated in this uppercase at the 0th position, because from this I would have actually subtracted capital A again to give me the value 0. So this at the index 0 initializes the index 2. Yes. Now for small b, this becomes the new letter, this becomes 3, and then capital B, I think I'm missing a small c, right, somewhere? Yeah, there is a small c actually in this. Yes, there is a small c over here. My mistake. So this is C, this is B, and this is C. So the indexes now are 4, 5, and this is 6. So now for capital, you would have now updated for small c in the next time. So small c gets updated with the value 4, right, at the second index, or indirectly at the third index if that would have been a one based indexing. Then over here you update this with 5, and then you update with this 6. Now you can see that the pair of the letters individual representation in lower and uppercase, both positions don't contain -1. That means I get a very simple idea that if both are not -1, it clearly means that both letters are existing. I mean, the letter in its lowercase format and its uppercase format, both of them exist somewhere in the string. Alright, so pretty simple approach. What am I going to do? I'll show you the code piece now. Right, you take lowercase, right, you take uppercase, this becomes 26, -1, -1. And now you can start your for loop from 0 word.size I++. If I now check is word of I greater than equal to small a and less than equal to small z, that means this is a lowercase letter. If it is, then lowercase of word of I minus small a is equal to the letter I. Alright, or index I. And similar goes for uppercase. Alright, now what I can do is take an answer is 0, begin this for loop from 0 to 26 only, because I have maximum 26 positions to check with a pair of small a, small b, capital B, so on. Now if I say both of them are not -1, that means both positions are not -1, that means there is an existence of the small part of it also and the upper part of it also, so I'll increment my answer. And now I will return my answer. Alright, so pretty simple, right? Pretty simple, good to go. Now what about time complexity? I can see this loop is going to run maximum in O of n order, and this loop is going to run maximum in O of 26 order, right? And then I have some space also. So if I simply talk about first time, I can report time as O of n plus 26, right? which is still very low because n is maximum going in 50. So this iterations would, whatever is the superseding iterations in this, that would be the max case. In maximum order, this would be O of 50, right? If the string is actually superseding, then O of 50 is the maximum iterations. And what about space? Now I'm using extra space, right, to calculate the index values. So I can say 26 is a good size. 26 for lower, 26 for upper, but you can call this as 2 into 26, from which you can remove the constant factors. You can say 26 is the I think order of saying space complexity I would utilize to actually store these indices. All right. So pretty simple problem, right? Like this problem doesn't even require a lot of discussion, and same goes to the next problem, right? So if we have well understood the first problem, the second problem is like the variation of the first problem, because you can even see this, that the first problem has the question name as count the number of special characters 1, and then this is 2. Alright, so I think we are good to go on the first problem, right? Basic index storing and basic returning if I find both indexes not -1. Now I have used this piece of code and just used a bit modification in the second question, right? How have I done this? Let us read the second question. Now the second question is also almost same. It's saying you will be given the word. You will be said that if a letter C is called special, it is called special if it appears both in lowercase and uppercase format. So up till here, the question is same as the first case, right? Letter C was special if it was appearing both in lowercase and uppercase. But they have just added this condition that every lowercase occurrence of C should appear before the first uppercase occurrence of C. Or if you say every lowercase occurrence of C, what does that mean? If I add to this question and I say every low occurrence of C should be less than actually the first occurrence of upper C. Every low occurrence, every occurrence, or you can call this every occurrence, right? Every occurrence of low C should be less than first occurrence of upper C. Now, what about this statement? Like this statement is indirectly trying to tell you that last occurrence of low C, lowercase c, you can call this, should be less than the first occurrence of, you can say, upper C. Yes, isn't that what it means, right? If I say that every letter which is looking like small letter C, small, like C is the character, so let's say some small letter, if every small letter occurs before the first very occurrence of its bigger type or the uppercase type, then I can say that if you simply check the last occurrence of this letter or the character C, if it is less than the first occurrence of the upper C, then I know every occurrence of the lower character C would be before than the first occurrence of upper character C. Is that right? Like let's say in this question, let's say I'll talk about the first case. Then the letter is A, B, C, capital B and capital C. Now if I ask you, I have letter A, B, C, capital letter A, capital letter B, capital letter C. Indexes are 0, 1, 2, 3, 4, 5 and 6. Now if I ask you, tell me the last occurrence of letter A, small letter A, you will call this 1, you will call this 3, you will call this 4. And then what is the first occurrence of capital A, capital B, capital C? You will call this 2, you will call this 5 and you will call this 6. So now you know that 1 is less than 2, 3 is less than 5 and 4 is less than 6. That means all three are an answer. Why? Because if I say that every occurrence of small letter A fell before the capital letter A, that means if the last occurrence of the small letter A fell before the first occurrence of capital letter A, then I know everything of small letter A falls before the capital letter A. And I can see in this, yes, this was the last occurrence of small a and this was the first occurrence of capital A. Because they were having a less than relation, that means I could have said they both definitely exist, as well as I know that they are occurring in this second condition also, fulfilling the second condition also. Hence this is a special, this is a special, this is a special character. So I get a total count of 3 as my answer, right? So problem is, now you can understand, problem is a slight modification of the first problem. Now why have I said this like this? Like why have I said that I think I am going to use the first piece of code in the second piece of code? Now remember, in the Second, in the first piece of code, we were storing indices. Indices of simply saying if that word of I occurred. So if that was a small I, I'll store that in lowercase. If that was an upper, I store that in uppercase. Now, what about this? Can't I do the same with this? Just I would store the indexes or indices, you can say, for every letter, but I will make sure that I store the last indice of the lowercase letter and the first indice of the uppercase letter. And then when I'm able to do that, let's say I'm able to somehow implement this out, then what will be remain for me to check? In this case, you can see that the only condition I was checking looks something like this. If uppercase of I is not equal to -1 and lowercase of I is also not equal to -1, answer ++. What more would I have to check now? Definitely both of them should exist. So these two conditions are definitely there. And I would have just simply said, if lowercase of I turns out to be uppercase of C of I less than uppercase of C of I, then also do answer ++. Yes, this would have been the added condition to simply say that the last occurrence of lowercase should be less than the first occurrence of uppercase. So that means this piece of code can work with very simple modifications. Now, what can be that modifications looking like? Let us look at the code directly. All right. I would do the same with this lowercase, uppercase, done and dusted. Now calculate word. If I say it's a lowercase, definitely initialize this. But if it's a uppercase, see a very small difference. In this, what I was doing is, when I find lowercase and when I find uppercase, I will directly say, just make that current I to the storing position in the upper or lowercase. But now in this case, what I want is, I want the last occurrence and the first occurrence. So I want the first occurrence of uppercase and the last occurrence of lowercase. How do I do that? How can I tackle that? One thing is definitely I can run two loops, one from the start and one from the end, doing one time for the lower part and one time for the upper part. That also makes sense. But if I just want to do it in a single loop, right? If I want to be more efficient, what simple piece of code should I write? I should simply say that whenever I find a word of I that falls in the lowercase boundary, I am going to update the current I with whatever was already could have been kept at the lowercase array. How does that make sense? Let's say in this string only, you had A, capital A, B, C, B. So one time you could have said that initially everything over here looks like -1, -1, -1. Start off from the left hand side. When I receive a small a, update this with 0. But then when I again receive a small a, update this back with 1. So if I make sure that I keep on updating whenever I find a small letter a, I will make sure somehow that would help me make sure that in the lowercase letter array, every ith letter, if it is not -1, then it stores the last occurrence of its lowercase variant. Yes, because I have always made sure that I keep on updating. Even if it's a previous thing, I will still keep on updating. So this simple line of check makes me sure that I am storing the last occurrence. But in the uppercase, you don't want that. In the uppercase, you only want the first occurrence, and then after you need to stop. So if I need to stop indirectly, like saying that let's say there was a letter capital A coming back. So I don't want to update it back, right? If I update it first with small letter, capital letter A with the index value 2, if then I have a new index value 7 also which contains the capital letter A, I don't want to make this 7 again. So how can I do that? I can keep a very simple check with the initial values, right? If I think that it has already been updated to a value, then do you think I need to update it anymore? No. So what I'll do is I'll say only and only if the word of I minus capital A's index in the uppercase character is -1, then update it to the new index I. And if it is not the case, if it is already some other value, then don't make any update. If you don't make any update, then that would simply mean in the uppercase array, for every ith index, I am storing the first occurrence of its capital format. And then I can simply run this loop again of 26. And as I told you in the previous question, add on to these two conditions, add on this third condition also, where lowercase should be less than I, lowercase of I should be less than uppercase of I, which would have meant that it fulfills all these conditions. That is, it occurs in lowercase format also, it occurs in uppercase format also, because both were -1, both were not -1 values, and it also fulfills the condition that every lowercase occurrence of C is appearing before the first uppercase occurrence of C. Alright, so good to go. Now I have shown you with this example. Let me extend that to, let's say, one more example. Let's say this example. Alright, let's say this this word was A, B, then you will have capital B, C, A and B. Now if I would have asked you for A, B, C, capital A, capital B and capital C, initially everything was -1. Yes, initially everything was -1. Now what have I iterated from the left hand side on to the capital letter A. So declare this with a indice 0. This is 0, 1, 2, 3, 4 and 5. Now small letter B, update with 1. Capital letter B, update with 2. Capital letter C, update with 3. Small letter A, update with 4. And now small letter B, so I need again an updation because I need the last occurrence. So this becomes 5 on top of it. And small letter C is still having -1. This is small c, alright? This is small c and this is capital C. It still has -1. Now tell me, if you compare both of them, both are not -1 values, that means both are occurring. That's true. But do you think they are occurring with the second condition fulfilled also? You can see very well that the last occurrence of small a is actually coming after the first occurrence of capital A. So do you think you will get an answer from this? No. Similarly for this, although both were existing, small b was coming after capital B, or the last occurrence of small b was actually after the first occurrence of capital B. So do you think you will get an answer from here? No. And now similarly for this, in this only you can easily say that in this small c was not even present. Then do you think it's a special? It's definitely not special anymore. So I receive an answer 0. Yes, nothing fulfills my character and I can say that yes, I get the correct answer. Alright, now what about time complexity? Pretty simple, right? As previous as said, this is O of n and then this is O of 26. Now if I talk about time, then what will be the time complexity now? Simply saying O of n plus 26 as previous as before, in which you can actually write that it is going to fulfill the order of whichever is the bigger part. So I can call this as, I can maybe call this as max of n comma 26, whatever is the bigger part. Yes, and this is definitely going to work because even if like most probably n is going to be very big, but n is only big till 10 power 5 limit. So you know that the order of this is going in maximum 2 into 10 power 5 order, which is still within my boundaries. Now what about space? You are using space as two arrays simply, right? So this is 26 plus 26. You can call this as 2 into 26 or simply remove the constant factor and simply say this is 26 size of approximation of space complexity. Alright, so first and second question now become pretty simple. Why have I, now when I said that you could have implemented first question in a map format, definitely you could have done that. But this becomes a mental note for you guys, right? In Leetcode what happens is, there mostly time like even in Leetcode, even in other platforms, what happens is, there comes problem when they ask you two parts of that problem, with first being the easier part and second being some different constraint part. So it makes sense for me to create similar solutions because then to increase my speed, it is very sure that 99% of the time, the second part if gets implemented, then the first part automatically gets implemented. Alright, so just keeping that in my mental note picture, I was able to create similar looking codes. But then again, this piece of code could have been implemented with maps also, because this only required you to calculate map occurrences. Alright, sorry, character occurrences, right? But this could have been implemented, right? I think this is a good approach to implement this. There could have been maybe some small variation to this, but again, I think the best idea would have been to go ahead with storing indices because you need indices, right? You cannot go with the indices. Even in this, you could have applied map then, but again, that's an added complexity of maintaining a separate factor that is not at all required for us, right? Even with simply a vector, our thing is working. So an unordered map or a map could have again worked, but that complexity is something I should have not gone into. I can implement this with simple vectors of frequency type. And even for this becomes a mental note for you that frequencies it's a very viable solution to store frequencies in vector format because frequencies of lowercase and uppercase are maximum 26. Alright. So like decent question, alright, not very tough, not very easy. And first and second question are now solved. Alright. So let us look at the third problem now, right? Minimum number of operations to satisfy conditions. You are given a 2D matrix grid of m, n size, and in one operation you will change the value of any cell to any other cell, and you will call that as any non-negative number, and you will call that as the operation. That is one operation. Now you need to perform operations such that these two conditions are fulfilled. Now what is that? Are these two conditions? The two conditions are grid of I and j should be equal to grid of I plus 1 and j. That is, in the current column, every number should be equal. Yes, if I say that I want to make, like, if I say grid of I of j is equal to grid of I plus 1 of j, and this is fulfilling for every condition in that cell. So I'll say that would indirectly mean that every cell in the column is same. And then different from cell to its right, that means grid of I of j should not be equal to grid of I of j plus 1. That means only if the right exists, then I'll say whatever was you made in the left part, don't make it in the right part again. Right? For, like, let's say some index I, if I talk about in different terms, if I talk about, let's say, standing at some row, if in that row the number which you want to make, if in the previous row you have also made that number, don't try to make that number, or you cannot make that number. All right. So now, how do you think you can solve those? If you look at the cases, things are going to look pretty simple, right? Let's talk about this first case. In the first case, we can very clearly see that every column has same numbers, and every two pair of columns, you can say that the numbers are not same. So if you talk about these two columns, 1, 0, not same. These two columns, 0, 2, not same. Yes. So essentially the condition is to simply say every adjacent pair of columns don't make the same number, but in the same column make every column same, or every number same. So if I look at now the second example, from the second example, what they have said is minimum count is 3. How? Initially it looked like this. They argue that what they will make is, they will make this number 0 as 1. So this row becomes 1, 1. They will make this number, that is 1 initially, as 0. So this column becomes 0, 0. And then they'll make this number 0 again as 1. So this becomes 1, 1. So now you have 1, 1, 0, 0, 1, 1. Right? Something like this, right? On pen, I think it would be better. You will have something like 1, 1, 0, 0, and 1, 1. And to make this, you required 3 operations. And now you can see that no two adjacent columns match for their values, but in a single column, every value is same. So I took 3 operations, and that returned the answer to me. So problem has become very clear now, right? There is a grid, adjacent columns not same, same column, every number same. Do that by changing numbers, call that as an operation, minimize the count of operations. So now if I want to implement this out, what approach do you think comes in my mind? First thing many of you must have tried on your own, or must have come to your mind yourself, would have been greedy, right? A greedy algorithm. In a greedy algorithm, what you could have said is simply that I would have try to make the first column as the value which, like, let's say let's say there are 3 columns. All right, let's say there is column 1. All right, let's say this is column 1. All right, then there is column 2. Then let's say there is column 3. Now, if I would have argued, tell me, for the first column, which number do you think you should make? You would have simply said, I will make that number only which comes the most times, because that will require the lowest number of operations for me. Yes. Why would I have argued that? Like let's say in this first column, 3, 3, 3, 4, 2. These were the numbers. So you will have argued, right? You would have argued that I will try to make this all 3, because 3 has the highest frequency. I would require only 2 operations to convert this to 3 and 3, and I would have gotten the first row all equal. That definitely makes sense. And then I would have argued, next time I will go to row number 2. And in the row number 2, because I have made row number 1 as 3, so I will say I will not make row number 2 as equal to 3. I will try to make it some other number. So let's say I was able to make it some other number. By the same logic, I will try to find the best number which I think I can make it by greedy logic, which is not equal to the previous number, that is 3. So I will try to make it some other number, let's say x, where I'll say x is not equal to 3, and x has the largest frequency possible. Because if I take the x to be largest, x has the largest frequency, then automatically I would require the lowest number of operations. Now this greedy approach might seem right at first, but the argument is, you cannot apply this greedy approach, because the failure of this greedy approach will be in cases where it looks like this. Let's say you had 3 rows and you had calculated your answer starting off with arguing that I will make my first row to be the number which has the highest frequency. Let's say in the first row the numbers were 4, 4, 4, 3, 3, 3, 2 and 1. So now you would have argued that I want to take the best answer. Now in this case, you can very clearly see that taking 3 or 4 both have the highest frequency, that is equal to 3. Even 3 has the frequency 3, 4 has the frequency 3. So which number should you take? The argument is, which number should you try to make? If you actually try to make, let's say you argue that I'll make this, let's say I'll go ahead with 3. Then I could have argued that, what if taking this current 3 was wrong? What if the next vector, this next row had the, let's say in the next row, you could have, if you have taken the condition to make this all 3, then this row, every number in this row looks like 3. Let's say in the next array, the array was looking like 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 1. Now tell me in this, don't you think the best condition would have been to make the whole column as 3? But can you make this equal to 3? No, because the previous column you made as 3. So you will never be able to make this column 3. So you would have next argued, alright, that means I could have taken 4, right? It would have been viable for me to take the first column all numbers as 4. Yes, because if I would have taken that, I would have received a count as 5 to convert all these 5 numbers to 4, and then I could have made this next column as 3 because it had a lot of 3's in it and only a single number 1, so that would have reduced my operations drastically. We understand this? Yes? That means a greedy logic does not work. Just simply calculating the largest frequency and then trying to brute everything out is not going to work, because you never know which path you should follow or which appropriate number you could have taken in the current column, so as to say this would have never gotten me a wrong answer in the next upcoming future. That means this solution cannot be solved by greedy. Yes, we just saw it cannot be done by greedy, because there can be multiple paths to create the shortest possible answer, or multiple ways you can actually figure out in the next column what numbers you should take. So you need to form a solution which considers all possible or all possibilities of answers. What do I mean by this? What do I mean by this is, for the first column, things are not going to be a problem. For the first column, I would have argued that the maximum numbers I have in the array, in the grid, are 0 to 9. That is, every number is either a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So for the first column, I would have argued, let me calculate the shortest number or the smallest number or the minimum lowest number of moves I would require, moves or operations I would require to make this first column wholly 0 or 1 or 2 or 3 or 4 and so on, or 9. Let me call this as my moves array. This is first column's moves array. Now when I would have gone to the next column, I would have said, because I want to check all the possibilities of creating the second column's numbers, I would have argued that let me brute out and ask myself, if I fix to make the second column a number equal to, let's say, 0, if I fix that I am going to make this column, second column, as 0, that means I am going to check whether what would have been the lowest number of operations in the previous column moves where I would have omitted to make the previous column 0. Does this make sense? If I want to make I'll repeat this again. If I want to make my current column as 0, then that means the previous column cannot be made 0. So whatever were the number of possible moves for every other answer except 0 stored in this moves array, the minimum of that, whatever was the minimum, let's say in this first array, I am talking about array every time, don't get confused with that. In the first column, in the first column, the number of moves to make this first column 3 was the lowest. Let's call this some small number mi, smallest number of moves. Then I can argue that if to make this all 3 and now to make this column 0, the previous number of lowest moves excluding the column to make previous column as 0 were, let's say, mi, then to make this current column wholly as 0, the moves would be simply the size of this column. Let's say the size of this column is actually like let's say I have n cross m grid, so I'll have a total of n rows. That means size of this every column will be n. So I will say this as n minus frequency of 0. That is the number of moves I have required to convert this whole column, plus I can say whatever is the previous number of moves I just calculated, that is mi. This will get stored in the, let's say this, I will call this moves array as previous moves array, and I can call this as a current moves array. So I can say current moves array, I can call this as current moves array of n, I can call this as of x becomes, or 0 becomes n minus frequency of 0 in this column plus whatever were the minimum number of moves that were transported from the previous column, considering I took that minimum number of moves when I excluded the possibility to make the previous column 0. Do we understand this? Now, if I continue this type of operation for every column, that is, I first, like I did this for x equals to 0 for the second column, I will do this with x1, x2, x3, so on till x9. And then I can shift my focus to the next adjacent pairs. So I will shift my focus from column 1, 2 to 2, 3 and do the same process again. I will now try to calculate the possible answers for creating the third column as x values 0 to 1, 2, 3, 4 to 9 by making sure that if I create it to be any number x, if it becomes any number x, then I will take the previous number of moves mi from the column 2 previous, like I'll call this as previous moves array, this is current moves array, by considering that I did not make the previous column as x, because if I would, then that would have violated my condition. If I do this every time and I use this relation in a general relation, I call this f of x or rather f of x in that current column, then don't you think at the very end, whatever is the, at the very end of my array, whatever is the current number of moves vector which gets stored in the current, which denotes the last column's total possible number of moves to create all numbers x, whatever is the minimum out of these operations, to be very particular, 10 possible operations to create number 0, 1, 2, 3 separate, right? I can call this as OP1, OP2, OP3, so on, OP10. Whatever is the minimum out of these 10 possible variables, don't you think that is going to be the answer? Yes, because I have you can call this maybe like this actually kind of like, you can call this as a DP approach, right? Kind of a DP approach. Because what I'm doing is, I am using the previous state of answers to calculate the next state of answers. Whatever were the previous state of answers of all possible x's, I used that to calculate the new states. Simply by arguing that in the new states, for calculating all possibilities for new states, every new x, I will first find the best possible viable minimum operations from the previous states, considering I did not make the previous column as x, and then add upon that to the current columns moves for x. Is that right? That would have given me the correct answer. Now, things might look confusing over here. So best thing, run on the dry case, right? So I'll take this answer only 1 comma 1 comma 1, and then this was 0 comma 0 comma 0. This was the array given to me, right? So I can make this as column 1, right? This is column 2. This is column 1. You can take this as column 2, and then you can make this as column 3. So now what I'll do is, I am standing at column 1. So for column 1, I don't need to do anything. Everything starts with column 2 comparison with 1, 3 with 2, and so on, so on. So for column 1, I can simply calculate the answer for every possible solution. So I'll say I have my previous moves array. Everything is 0 in this, but when I finally calculate my answer, I'll say to make this whole array as 0, I will require 1 move. To make this whole, not array, again I'm saying array, this whole column 0, I'll require 1 move. To make this whole column 1, I'll require 1 move. Then to make this whole column 2, I will require 2 moves, 2 moves, 2 moves. Then this is 2, 2, 2, 2, 2. Yes, total 10 possible answers for index 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Yeah, right? 10 possible answers from 0 to 9 ranges. So 10 possible storing moves stored. Now I move on to this column over here. This column's array, I can call this as current moves. Everything is initially 0. Now I start declaring. I argue that if I want to make this whole column as 0, then what I'll do is I will find the minimum value excluding 0 from the previous moves. So I'll say minimum value is, I cannot take this index anymore. So out of all these values, the minimum is 1. So that means I will take this as 1 plus, to make this whole current column as 0, I will require 1 move. So I will declare my current moves to be 2. That is, up till here, up till the ith index, the best possible answer to create is 2 if the last column was 0. Yes, now I'll repeat this again for the next process. I will argue that what if I wanted to make this column 1, fully column 1. Then I will argue if you want to make this whole column 1, then the previous column cannot be 1. If it cannot be 1, then get the best possible answer of moves excluding 1 or at the index 1. So this is 1 moves, this is 2 to 2 moves, best is minimum is 1. So same answer again, copy paste it. I'll say 1 plus, to make this whole column 1, I will require 1 move, that is 2. So I'll store 2 moves now. Now what about next? To make this column wholly 2, I will say what is the best feasible answer to make previous column. Now previous column, I cannot make it 2. So other numbers I can make it as 0, 1, 3, 4, 5, 6, 7, 8, 9. Out of the best possible moves, I can take either 0, either 1, not a big deal. So taking actually this as 1 moves. So I get 1 move from the previous column plus current moves to make this wholly 2. Yes, replacing all 2 numbers as 2, 2. So that is 2 moves. So that is 2. This becomes 3. So I store the answer as 3. And similarly, you can argue that I will get answers for the rest 3 numbers also. Will I not? And now what I can say is, I was now talking about these 2 columns at a single point of time. These 2 columns. I will now shift my focus to these 2 columns. So I will now say that my previous moves array no longer exists because I don't require my previous moves array at all. And my current moves array becomes equal to my previous moves array. And now I create a new current moves array to be calculated till this new column I am talking about. Now same process again. I will find answers as 3, 4, 4, 3, 3, 4, 4. This is what is going to be the current moves array now. Yes. And now when I fully exhausted my, I should say, calculations, and my current moves array, like I would have actually in the piece of code, this current moves array would have now become previous moves array again. In this array, whatever is the lowest count of operations, wouldn't that have been denoted as a main answer? In this lowest number is 3. And 3 is your answer. Yes. Why 3? Because what am I essentially doing? In a very state formation DP format, I have declared that every time I have 2 arrays, previous moves and current moves, it denotes what is the minimum number of operations to make, if I'm talking about the current moves array, to make ith column X. This is getting stored in current moves of X. Is that right? And I am going to do this for all the columns. So when I reach at the end, the nth column, or actually you can call this n minus 1th columns, all possible answers for x's, minimum out of those gives me the viable answer. Alright, so this no longer looks like a greedy algorithm. I have no longer fixated that I am going to take any single number, but rather I have taken all possibilities. So although like there is still a bit of greedy to take the minimum possible answer from the previous state, but this is not greedy in that sense where you can say that it's pure greedy when I actually calculate a very naive solution of taking simply largest frequencies every time. Because initial argument was, again I can repeat, is if you do that for every column, there is not a surety that you end up with the best possible lower number of moves. That is why you need to every time calculate all possibilities of creating X for every column and do this for every state till the n minus 1th column and then return the best possible answer. Alright, so I've done this for the second case. You can run this actually for one of your own cases and you will very clearly see that this problem is actually how it should get solved. Alright, I think there are similar problems like this. There is I'll say this in video only, there is a problem called painting the fence problem, which is a similar 1D problem of calculating possibilities. If you actually search that out, painting the fence on GFG or even on Leetcode, you will get this problem again. So this is just like that problem, and the same approach has been used to calculate or store answers of previous states and pass it on to the next states. So kind of DP. And why I done this? Because all possibilities must have been explored. So now we can look at the code part now, right? Once you have understood how we are implementing this out, code is going to be very simple. First, I'll calculate n and m, simply grid size, grid.0 size. Frequency of row. So I'll create a 2D vector, right? Called frequency of rows. Sorry, not frequency of rows. Sorry, this should be actually columns, right? Frequency of columns. And then, right, this is column. This is also column, right? Let me submit this out and let's see. Yeah. So frequency of columns. What will I do? I will run an iteration from 0 to m, that is going to every column. Calculate a current frequency vector of 10 size with everything 0, because I know maximum numbers are 0 to 9. Increment current of f by grid of I of j, so simply calculating frequency, and then push back this current f vector in frequency of column. Why do I need that? I need 2D, I am pre-computing 2D columns frequencies, because everywhere I saw that I needed every column's net frequency sums. That is why, with which I could have actually calculated that if I want to make this current column as x, what number of operations will I require? Yes, n minus x I would have required, frequency of x I would have required. Common sense, right? That is why I need that. So I have pre-computed it, right? Now I have calculated a pre-moves array, starts with 10, 0. I begin off with the first column. I create a new array, that is current moves, that is equal to the previous moves array. Right, that is just equal to the previous moves array. Or you can even call this as, like, you can initialize this as 10, 0. It is not going to be a big deal. All right, like simply creating a new array per se. This is still going to get accepted. Yes, a new array current moves, right? 10, 0. I don't know why I wrote that, right? Now what I'll do is, I will run a loop from 0 to less than 10, and I will, look at the variable, current make. That is, what is the current column's number I am trying to make. If I'm trying to make it 0, 1, 2, 3, so on till 9. So this is that number. Now to make this number, I will first calculate the before minimum operations. So before minimum variable is int max. I will again run an iteration in the previous moves array. So I will run an iteration on previous nums from 0 to less than 10. Then I'll say, is the previous num equal to current make? Then I'll continue. That means I cannot, that makes sense, right? If the previous number was something and the current number I also want to make is equal to that, I want to continue. But if I don't continue, then what I'll do, I'll calculate the lowest minimum number of moves. How? Before min gets minimalized with previous moves of pre-min, before min. Now when I come out of this loop, before min variable is going to store the lowest number of moves to make any number that was not x in the previous column. So in the current column, the current moves of current make gets initialized with or gets a updated value with before number of moves, as we just saw, mi plus n minus in the frequency of column j of current make. Is that right? Right? Why J? J is the running column and then current make is the current number. Now when I come out of this for loop, I will make my, just to store new states, I will make my current moves as my new previous moves and I will move on to my next answer. When I come out of this whole loop, I would have calculated in my previous moves array the best possible answer for all x's till the n minus 1th column. So the minimum element out of the whole array in pre-moves gives me the best operations to convert this whole grid into whatever was needed by the given conditions. Alright, I hope this makes sense. Now if I submit this out, you are going to get a accepted solution. I have done this many times. If I talk about the time complexity now, you are running an O of M solution, right? This is O of M loop. Now this is O of N loop. And then pushing back is also like going to take a bit of time, but then again pushing back is so small, right? The vector size is so small to push back. You can call this as simply pushback of 10 maximum size. So I can call this as actually, I can write like up till here the time complexity somewhere looks like very detailed time complexity M plus, right, M into, this is N plus 10, which is actually simply like bigger order is N into M. Alright, it's a simple frequency calculation. Now inside this is O of M, right? Now inside this is O of 10. So this is O of 10. And then again inside this you have O of 10 solution. Yes, you are doing this again, O of 10. Alright, so what do you think is now the time complexity for this loop? You can call this loop as O of M into 10 into 10, or simply M into 100. Plus, there's going to be a bit of time complexity to copy this array. Size of this array is 10 actually, so you can call this copy array size as 10, but that is not going to be a big deal for me, right? So I can actually call this as something that gets pre-excluded. So now what do you think is my time complexity now, right? This can be actually written as, to be very specific, 100 plus 10, right? Because 100 is this number of moves up till here, and then 10 would be the number of moves to actually copy the array. Just like copying the array is actually like you can take some complexity for that also, but it's not going to be a big deal. That is why I excluded it. So this is like simply saying M into 100 is a good order for this. So, and then finding this minimum element. So like even for running this STL function, this is O of 10. So overall, if you look at the time complexity, it's very small, right? Time complexity, if I calculate time complexity, you have O of N into M solution there, then plus M into 100 solution there, then at the end, some very small 10 iteration solution there, in which very clearly the superseding term is N into M, right? And N into M, since N and M both are in 1000 order, N into M is going to give me a worst case order of 10 power 6. Now, do you think it works? Definitely it works, right? Why will it not work? It is definitely going to work because it is well within my iterations. Now, what about my space complexity? O of, you can call this as calculating frequency of columns. Because I calculated frequency of columns and its size was, you can say, every columns into 10. So frequency of column was having every column, that is, you can say N, right? M, every columns into 10. So frequency is what is giving me the main complexity, plus I can call this as frequency moves array, that is also 10, plus current moves array, that is also 10. So overall, M into 10 is a good order to report. Is that right? Now, don't you think space and time both are well within my boundaries? Of course, they might be right. They must be right. Otherwise, this solution was not getting submitted. Every time you can say, I accept this, I submit it out, it gets accepted. That means this solution is a correct solution. It is the best solution in its time complexity also, and definitely it works. So taking all possibilities is the way to go. Alright. So now at a first glance, this might not hit you, right? If you make a greedy solution, like even I must have made a greedy solution myself by small experience, and I would have definitely gotten a wrong solution, right? But if you must have done that, you would have very easily understood what was I trying to actually tell you previously. To calculate all possibilities is your only possible answer. If you don't calculate all possibilities of answers, you will definitely end up with a greedy approach, which is not going to every time result to you the best possible answer, right? That is why the answer to this problem is actually this sort of a solution where you maintain previous and current states or previous and current moves and do this for all possibilities. All right. All it's got submitted, and I think we can move on to the fourth problem now. All right. So let us discuss the last problem for this weekly contest 394, right? Now, this is a very interesting problem, right? This is a very, very easy and very simple problem once you get the idea of it. And this is a very important idea, which is a very common sense based idea, and it gets followed in like I have seen many questions which actually follow this basic implementation. All right, so let us read the question. You are given an undirected weighted graph of n nodes numbered from 0 to n minus 1, and the graph consists of m edges represented by the 2D array, and the edges format is ai, bi, wi. So simply there's a graph given to you, right? Edge between nodes ai, bi with a weight wi. So not a problem. Undirected weighted graph. Consider all the shortest paths from 0 to node n minus 1 in the path. You need to find a Boolean array answer where you think answer of I is true if edge of edges of I is part of at least one shortest path. So like if you say that I'm standing at a current edge I, and that edge is part of at least any one shortest path you could have followed from the node 0 to n minus 1, then you make answer of I as true, otherwise you keep it as false. So in a first go, the problem might seem very like tough to implement, right? What about like if I find a brute approach in this, do you think it should work? Like if brute approach comes to my mind, I'll maybe say that I would have gone to every edge, right? I would have done a for loop for every edge. Let's say this is the ith edge, and then for this ith edge, how could I have actually implemented this out to whether check that is part of that or not? Maybe I could have stored all the shortest paths that come from 0 to n minus 1, and then maybe I could have iterated in that. Maybe to do that, like storing all shortest paths would have been very tedious, right? Storing all shortest path means I could have implemented a shortest path algorithm, preferably some popular algorithm known as Dijkstra, right? Dijkstra is a good algorithm to implement. By Dijkstra algorithm, I could have maybe calculated all the shortest path possibles, then I would have gone to every shortest path, checked whether this edges of I is present or not, and then I could have returned true or false accordingly. Now, do you think that's going to be a good complexity to follow, right? If I look at the constraints, just in iterating of this edges are m, right? So m is in order of 10 power 4 max. So iterating in every edge, that's 10 power 4. Then you implement Dijkstra also inside that. That's minimum of, like even if you implement Dijkstra, like the worst case Dijkstra, the best case Dijkstra running with a priority queue, right? In a priority queue format, you could have implemented this within, I think there is a E log V factor to this, right? So in that case also, you will still get a very high time complexity, right? But outside order would be in 10 power 4, inside order would be in 10 power 4 into log of 10 power 4. So overall order would be somewhere in 10 power 8, even greater than actually 10 power 8. And then that would have been something very tedious, right? You can very clearly see that I will never get this as a right solution. I will always get a TLE. So that means I need a better approach than this, right? I need a better approach than this. Preferably what will I try to say is, I will try to think in this direction that like this is indirectly a query based problem. For every, I would have argued that it becomes a query for me to find whether or not I think edges of I is part of at least one shortest path. And if I'm able to answer this query very quickly, then I could have iterated in this edges array, and inside this I would have achieved a complexity that is so low that would have given me the correct answer directly. I would have maybe with some if checks or else checks, I would have directly gotten whether this edge is actually of the true case, right? Whether this edge is of the true case or if it's of the false case. That is, if it actually belongs to at least one shortest path or not. So I need some better approach than this, right? My mind is definitely running to optimize my solution in such a way that I am able to answer every query very quickly. So now to answer every query very quickly, I need to first understand some base mathematics in this, right? Some base observations in this, not mathematics, observation in this. All right, let us talk about that. Let's say there's a graph given to you. Let's say this is node A. There's a connection to, let's say, node B. All right. Then there's a connection to node C. Then there's a connection to node D. Then maybe E. And all right, the graph looks something like this. Cool. Now let's say I have the weights as 1, 2, 4, let's say 5, 1 and 2 again. Good enough? Or I think I should not draw my own case. This is going to be looking much better if I draw the main case. All right. I'm sorry. If this becomes 0, this becomes 1. All right. This becomes 4. This becomes 2. There's a connection to 3. There's a connection to 5. All right. Now there's a connection over here, here. Then there's a connection back also. And then I have some weights, right? Let me quickly mark them. This is 4. This is 3. Then this is 1, 2, 1, 2. then I have a 1 and 3 over here. So first hand most, right, what clearly I can picture. First thing I can clearly picture is, let's say I simply ask you the distance from the 0th to the n minus 1th node, the shortest distance you think. In this you can very clearly see that the shortest distance is going to be something that looks like 5. Yes, I could have maybe followed this path. This also gives me 5. Maybe even this path. This also gives me 5, right? Or maybe even something like this. This also would have given me, I think 1 plus 1 plus 2 and then back again, right? So I have almost like 2-3 paths that are giving me the answer 5. So not a big deal, right? I just have the 5 with me. Now, why have I calculated this 5? The query is to actually tell me that this is the, let's say this is the shortest distance, SHD, this is 5. What that means is, if now I individually talk about an edge, let's say I ask you, tell me about this edge. So this edge is made up of 2 vertices. This is one vertex, this is the other vertex. Cool? And then the starting vertex should have been 0 and the ending vertex should have been 5. Now what is necessary by common sense, that if I think this edge belongs to the path, there is one path, right? This is one path that goes something like this. There is one path that goes like this. If I want to make sure that this edge is part of this path, then that clearly means that on this path everywhere I have received shortest distances. So if I ask you that, tell me the shortest distance, I'll mark this with green, from the 0th to the second node, and the shortest distance from the node 5 to the third node. If I calculate this as shortest distance 1, shortest distance 2, and then whatever is the middle weight, let's call this W. So if I say S1 plus S2 plus W, this is the distance that was there, shortest distance that could have been there between the path connection from 0 to 2, 3 to 5, and then the middle part 2 to 3, connecting a whole path from 0 to 5. The sum of the weights that actually fell, that was S1, shortest path sum from 0 to 2, plus S2, shortest path sum from backside 5 to 3, and then this middle weight that gets added 2 to 3. If I know, if I argue that 2 to 3 belongs to some shortest path overall, then I know this should be equal to 5. Is that right or not? Yes. Why 5? What is 5? Isn't 5 shortest like SH, if I actually write this as SHD? Meaning, what is the argument? Argument is, if there is an edge u comma v, which is part of at least one shortest path, then the shortest path sum from 1 to u plus n to v plus the weight of u comma v edge should be equal to the shortest path from 1 to n. Or sorry, in this case, if I'm talking about zero based indexing, then 0 to n minus 1, not a big deal. So shortest path from 1 to u plus shortest path from n to v should be equal to, plus the weight of u comma v should be equal to the shortest path, overall shortest path from 1 to n. Does this make sense? Yes. So if I have understood this condition, by common sense, this condition makes sense, because I know that shortest path from 1 to u would have been the shortest possible sum of path following from 0 to, or this node 1 node, or let's say in 0 based indexing, this is 0 and this is n minus 1. You can call this n minus 1. This is 0 and this is n minus 1, right? N minus 1. Then 0 to this node u, shortest path, n minus 1 to this node v, and the middle weight should have together formed a shortest path. Yes, because if I have calculated the shortest path from node 0 to this node u, I have actually taken up a small segment of possible shortest path, possible original shortest path. And I have also taken a small segment from the possible original shortest path from the back side. And I have just linked both of them with a small weight that falls from 2 to 3. So this linking which is happening, if this link is actually existing to create a shortest path, original shortest path, or is giving me a possible shortest path, only then I will say that this link is actually part of a shortest path. And to make that for short, if I want to return true for this answer, I would definitely argue that that would mean the net sum you actually calculate on the shortest path, that is S1 plus S2 plus W, should definitely have been equal to the overall shortest path from 0 to n minus 1. So I think this argument is making a lot of sense now. Now on this basis of this argument, now if I ask you, can you calculate your answer? Can you say yes? How? Now what would simply be the question is to implement this out, right? I have understood the small condition. Now this small condition is going to help me a lot. How? If I now want to answer the query very quickly, what can I do is, I can run two shortest path algorithms. One can be called Dijkstra 1, right? You can call this as shortest path or right, Dijkstra 1, which would be calculated with a source as 0. Yes, source as 0. Next time, you can again calculate the same Dijkstra algorithm. Only this time you will say the source is actually n minus 1. So you would have made your Dijkstra call with the source as n minus 1. You can call this as Dijkstra 2. From both of them, you would have received a distance vector, shortest distance vector, distance 1. This would have been the smallest possible distance to traverse from 0 node to every other node. And then you would have received the same thing from distance 2. Same thing by running the Dijkstra 2 as a distance 2 vector. That is all the possible smallest paths values from n minus 1 node as the source. Now if I would have asked you, give me the answer for every edge, how could you have reported that? You would have said, let me go to edge a comma b. I would have first calculated the shortest path from 0 to a by simply calling the value, let's say it was kept over here, simply in a constant factor calling that value in distance 1 array. From n minus 1 to b by calling that, let's say some value was kept over here in the distance 2 array, again in constant time complexity. Add both of them and then add upon that the weight of a comma b. And if both this net sum that falls, this net weight that falls is actually equal to the dis value, let's call this dis value, that would be the shortest path from 0 to n minus 1. Then I would have said this edge is a viable edge, mark this edge's index as true. So I would have done this for simplicity. I would have first done this with a comma b, considering I travel from 0 to a and then n minus 1 to b. Then I would have again done this for considering I would have traveled from, let's say, 0 to b and n minus 1 to a, and then add that up and then along with that weight. So both conditions could have been possible. Yes, it could have been a case that the current edge which you are talking about, that current, let's say let's say I'll talk about this edge only. All right, the diagram has become a pretty I think dirty diagram, but you can understand this, right? Let's say I'll talk about this edge. All right, focus your power on this edge. 1, 2, 3. Calculate from 0 to 1 the shortest path, that is 4. Yes, so I have 4 plus. Calculate from 5 to 3, this is 3, plus the middle edge, this is 2, so 2. What does this become value? This value is actually 4 plus 3 plus 2, which is actually equal to 9. So you will argue that edge 1 to 3 is not an edge which falls in shortest path. But my argument is it does. It does. You can even see that for this index 1 to 3 edge, the answer is true. Why? Because the other edge case can be, rather than seeing this with 0 to 1 and 5 to 3, do the opposite. Let's talk about calculating the smallest distance from 0 to 3. That would have been 1 plus 1, that is 2. Plus 5 to 1, that would have been 1. Plus the mid part, that is 2. This turns out as 5. And this is actually the shortest distance, 5. So now do you think it definitely falls in at least one shortest path? Yes, it does. So for edge case, what will I do? I am going to do this operation twice. First saying I would have traveled from 0 to a to b, and then b to n minus 1, or 0 to b, b to a, and then a to n minus 1. So both conditions fulfilled. If either one is true, I will mark that edge as a possible edge, because that edge definitely falls in any one shortest path. Now, what do you think is the time complexity of this piece of code? Now, do you think I am able to answer everything very quickly? Yes. Why? Because what I could have done is, I could have implemented the best possible algorithm of Dijkstra is achievable is E log V. Yes, E log V, which is E number of edges, V is number of vertices. So E is 10 power 4, V is 10 power 4, so this is definitely within my boundaries. Do this once for dichastra 1, call this dichastra 1, calculate distance 1 array. Do this again for dichastra 2, calculate this distance. So overall time complexity is this plus this, which is still this. So this is E log V, still within my boundaries. And then for every edge, let's say the total count of edges is M, make a loop in the edge array, and then you can very clearly see that in a very constant factor, I'm able to return my answer. Because in the distance per array, already there are values computed. Distance to array, there are already values computed. So I just need to add both of them, add the weight, and then check whether it is equal to the smallest path from 0 to n minus 1 or not. So don't you think that's going to be a constant time complexity? So now overall time complexity would have actually looked like E log V plus E log V plus E, where number of edges, which would have been simply as the superseding term E log V. And this is definitely within my boundaries because I know E log V is definitely working, because like E is in 10 power 4 order, and then log is also would have been in 10 power 4 order. So you would have gotten a 10 power 5, like 5 into 10 power 4 into, I think 10 power 4 is approximately 16 iterations something in log power. So this is the approximate time complexity, which is well within my boundaries, right? Within my 10 power 8 complexity, definitely faster than the brute solution I was discussing. So that means I am good to go. The whole problem has now fully boiled down to the idea, again I repeat, to imagine that for an edge to be part of at least one shortest path, it is necessary for it to have this condition to be true, that is either traveling from 0 to that one node of that edge and from n-1 to the other node of that edge, along with that added sum of weight, should give me the shortest path distance, or vice versa. If any one is true, then I know I can picture that edge as a connection between two other possible, paths, S1 and S2, which could have resulted in a net path of being the shortest path type. Good to go. Now everything falls down to implementation. Alright, so this is crude implementation. Take the adjacent array, take the edges, right? Push back this and this. Good to go. Now distance 1, distance 2 calculation, right? Now I will initialize the priority queue Q. Now I will do one time the dichastra. I'm going to do this dichastra. You can see this dichastra part. This is going to be for the source 0 dichastra. Yes. How? I would have pushed inside my queue. First, I maintain the weight. So this is 0, 0. That is the node. Distance 1 of 0 gets initialized with 0. Everything was max initially. Now in the dichastra, this is very simple dichastra. I'm not going to go in a detailed part of that. I will pop out every node, and now I'll check if distance of 1, that is reaching of the child, is greater than the sum of the current path plus this weight. Then I will update it and push it back in the queue. So basic dichastra. Now I will do this again for the source as n-1, and I will save my answer in distance to array, right? By pushing in the queue 0, n-1, declaring distance of 2 n-1 as 0, and then doing this the same. But now what will be my main algorithm? I will first calculate the actual distance, that is dist 1 of n-1, that is simply saying 0 to n-1, what is that distance? Calculate an edges size, that is m. Then a boolean answer array, initially everything is false, of the m size. Now if I think that from 0 to n-1 there is no path possible, that would have been meaning that this value would have been int max, right? Initial value int max, still int max. So I would have said return answer. That means nothing is traversable, nothing is possible, simply return the answer as it is, and every answer is false in that. That means you are not having any shortest path, then you will never be able to answer true for any edge. But if that is not the case, if I don't do this, if I don't execute this statement, then what will I do? I will go to every edge. So 0 to m less than m, take out the edges A, edges B, and then I will calculate the dis1, that is distance of 1 from A, that is, this would have been shortest path from 0 to A, right? Similar, this would have been shortest path from n-1 to B. And then if I think both of them are not int max, that means both exist, and their sum plus the weight is equal to the original dist, then I think this answer is true. And then I'm going to repeat the same thing by swapping A, B and calculating this again, right? If after doing both of these operations, answer of I anywhere becomes true. That would mean that this current edge is a part of at least one shortest path. Is that right? And now if you can see, if I submit this out for you, right? If you see, if I submit this out for you, this is going to get accepted. This is going to give me a right answer. Is that right? So this definitely works, right? Very basic question now. So we have clearly understood the idea behind the problem. Idea was very simple to implement. If I've understood I have to implement dichastras, can't implement two dichastras. You can. But the actual observation was very crude part in this problem. That is to understand that there could have been a relation like this. Shortest path to that edge node 1, shortest path, another shortest path from the back other node to that other node, plus the mid edge connection or weight could have resulted in a net shortest path if it is equal to the actual shortest path value. Alright. Alright, so I think pretty easy problem now. Now what about time complexity? As we discussed, this is going to have a E log V factor, right? This is also going to have an E log phi factor, E log V factor. And thus inside this you are running a very simple loop in, you can say M size or simply E size, which means time can be reported as we discussed over here, TC is O of E log V into 2 plus E, in which superseding term is definitely going to be E log V. So I can say overall time complexity is going to be E log V within my boundaries, and you can see it is definitely was within my boundaries, otherwise I would have gotten a TLE. Now what about space? In space you are using two distance arrays. There's also Q. So Q size maximum could have been gone in edge condition, so I can call this as E plus the distance array is dependent on n nodes, you can call this n nodes or V rather, V vertices, right? So I can see EV plus E is a good time complexity, space complexity to report for this question. So both are part and parcel of my answer, and both are definitely within my boundaries. So I know question is working, right? So again, takeaway, very small modification of dichastra. Understand the short path algorithm, and then implementation is very easy. All right. So I think comparatively today's contest was pretty easy, right? Even for the first, second, third and fourth problems. And you could have gotten a very good rank if you were able to have basic observations in this contest. All right. So I hope you liked the video. Thank you for watching.